Okay, good morning, everyone. Today we are continuing our lecture on the linearized gravitational wave theory. In the last expression, we obtained a solution for the linearized gravitational wave theory, which was analogous to the form momentum of classical electrodynamics. Well, we want to look at some of the properties of this solution. We obtained a formula such as this being equal to that, which could be written as that, given this expression, which was one of the formulae we obtained in that lecture. And so if we were to take the four divergence of this expression, z mu nu equal to that, we will obtain z mu nu comma mu equal to this. Because if you remember, this z sigma sigma might as well be just z without any indices, or z mu mu. But if I were to differentiate the whole expression with respect to x mu, then this conical delta changes the mu to nu, and this is what I have here. And of course, T mu nu differentiated with respect to S mu is 0, and this is the conservation law for the energy momentum tensor which we used on that day. Of course, so this therefore means that this being equal to this equal to 0 implies that, or in fact is equivalent. So this being equal to 0, or this conservation law, is equivalent to this or that. Z mu nu bar comma mu equal to 0. Now this notation here we introduce by writing it as this. Any such notation as this in GR, this will be peculiar to Kipton's book and I believe Joseph Weber. Z mu nu like this with a bar means z mu nu minus 1 over 2. Maybe here a conical delta or some metric tensor. So mu nu z. Well, to define this, let's just make this all transparent. We may, for instance, consider a situation whereby from the Einstein field equation that this is given by that, we can see that when we consider the Einstein field, when we raise the indices, mu nu, mu nu, mu nu, if we contract mu and nu, we therefore obtain the trace of this expression. And by contracting them, of course, setting them equal to mu mu, for instance, all the indices being equal, this is equal to 4 as usual, divided by 2, we get 2 here. So that in the end, G mu nu is equal to minus R. Of course, by R minusing 2R, we have here minus R, which implies that the trace of the Einstein field tensor is equal to minus the trace of the Ricci tensor. In other words, we could use such a notation as this. G R bar equal to minus R. This implies that G mu nu is equal to R mu nu bar equal to R mu nu minus half G mu nu R. So this is just the way the definition goes. What it tells us in essence is that you could see the Einstein field tensor as the same, almost as the Ricci tensor, except for the fact that the trace this time around is reversed. So the Einstein field tensor is the same as the Ricci tensor with its trace reversed. So if we use this kind of notation with R bar, or R bar in this case, R bar mu nu, to denote every such expression as this, then you can now understand our notation here for Z bar. So you can see the only difference, of course, in this case is that we have raised the indices here. So the indices here, mu nu, but the bar is like the original tensor minus half some conical delta times the trace of that tensor, or some metric tensor. In this case, of course, is the Ricci tensor minus half the metric tensor times the Ricci scalar. So this is what we call the trace reversed Ricci tensor, or just the same as the Einstein tensor. So defining the trace reversed metric perturbation, just like we've explained with this notation and shown with this notation here, defining this with the trace reverse metric perturbation, we have that. So we could, for instance, define some reverse trace metric perturbation by saying h mu nu bar equal to h mu nu minus half the metric tensor, of course, times the trace of the metric perturbation, which is our h, where the trace of the metric perturbation might as well be represented as h alpha alpha, beta beta, or whatever, just repeated, or equal to that contracted with this. Now, so similarly, in that case, one of the things we obtained then was the harmonic coordinate conditions. The harmonic coordinate conditions, originally, of course, if we were to use this expression, if not in the linearized theory, this would have been G mu nu. So, but from this, using our linearized expression for the Christoffel symbol, we obtain such an expression as this. And you can see, of course, it's h mu nu comma mu, which is equal to half h mu mu comma nu. What we can do here, for instance, is we could introduce a chronicle delta, such as this mu nu comma mu instead of being comma nu, this time is comma mu. With the idea that this chronicle delta can as well be used to change the mu back to nu. And we put mu mu here, which isn't really necessary. For instance, you can see that okay, so with that now we could define this to be equal to that instead of this. And if I should take this to the other side of the equality sign, I'll obtain this being equal to 0. So the idea is to bring both terms under the derivative with respect to x mu. So this then comma mu is equal to 0. It's just the same as that. But you can see that in the end, of course, yes, we have obtained this. We stated before in our presentation that eta mu nu is indeed equal to the chronicle delta mu nu. And so with this now, like we said, we of course showed that the metric tensor with one of the indices raised, that's the Minkowski metric, is the same thing as the chronicle delta, written in that form. And so of course with that, we might as well replace, okay, I think we already did that. So we replaced this with that here. Excuse me. So with that, we can say that this expression equal to 0 is the same as that. Where, of course, you can see we have identified this with our trace reversed metric perturbation with the mixed indices or mixed rank for the contravariant and covariant case. Hence, the notation z bar mu nu on top. So you can see now with this explanation how we came about with this notation right here. Now, we said also from this expression here, we obtain such thing as z mu nu comma mu equal to that. And you can see, of course, we are able to show that this is the same thing. If we were to put this to the other side of the equation, we will have to introduce a chronicle delta that would be delta mu nu, which will change the nu here to mu. So if I had a delta mu nu here, for instance, so let me just do that. Delta mu and nu, sorry for that mutilation. I'll have a mu, but then in that case, I wouldn't have any indices here, or I might as well just put them sigma. With the understanding that delta mu nu, with the understanding that the delta mu nu, for instance, here changes the mu here to nu, and then that gives us back what we had originally. But then, of course, if we were to push this to the other side of the equation, you can see that what we'll have in the end will be z mu nu, which, of course, we have written here, z mu nu minus half chronicle delta mu nu z. And that will be our definition for z bar. So again, this expression here is just the same as that. And so our solution, for instance, which was written as this, equal to that, satisfies the harmonic condition. This solution satisfies the harmonic condition because, of course, you know, if we were to substitute this h mu nu just by raising one of the indices, of course, we'll have to raise this index here too. If we were to substitute it into this equation, since this is true, then we know that our solution also satisfies that. And that completely illustrates the equivalence of this conservation law here and what we have written here in this form. So is either t mu nu comma mu equal to 0? This is just the same thing as z bar mu nu comma mu equal to 0. Now let's explain how this notation does affect our solution and notation in various ways, at least two distinct ways. The instant field equations, we have denoted ones to be written either in this form or equivalently in this form. And we, in our linearized theory for the gravitational waves, use this form. And of course, this was what we called z after we changed this to eta mu nu. We call this z, of course, sorry, looking at Wember's book, it is called S. Sorry, I want to make sure there are no confusions here. I think Wember uses S here. I choose S for something else, so I chose to call that Z. Now, with that equation, you can see we linearize. So what we call S, in the end, you can see that our equation here, Z mu nu, is actually the same thing as T bar, or whatever we may call that, because you can see this is T mu nu minus half G mu nu, T sigma sigma. So this, for instance, denotes some T bar mu nu, according to the notation we just defined now, where T bar mu nu is equal to that. And with this expression, we linearize the Ricci tensor in the first order, and then linearize everything else. Of course, that was how we obtained the solution. Now, one other approach you could use is instead to use this first equation. And apparently, this approach is used by Krypton in his book. So instead, you multiply this equation by 2, and so that you have 2 times the Einstein field tensor equal to minus 16 pi g t mu nu. Of course, Krypton always uses geometricized units in which g is equal to 1. And so in his own approach, or in their own approach, they linearize this equation. And so what they obtain in essence is something like this. So you can see that they linearize the equation with the Einstein field tensor on the left-hand side. Well, not a tensor, but just Einstein field tensor linearized on the left-hand side, 2 times of it, equal to here 16 pi T mu nu. But take a note now here that the T mu nu here isn't the same thing as the T bar here, which is actually what we used subliminally in our own case. And this was what we did when we linearized our Einstein field equation. If you recall, what we did was to linearize the Ricci tensor, yes, in its first order, and with that we obtained our solution, which in fact is this. This was what we obtained. This was what we obtained. But in Krypton's approach, looking at their book, either by Misner, Thorne, and Wheeler, I believe chapter 35 and 36, or you can also look on YouTube a set of lectures which Krypton is giving, usually tagged the gravitational waves with Professor Krypton on YouTube. Very good sets of lectures which I believe are very, very valuable for anybody seeking to understand gravitational wave theory. So the point here is I'm just trying to make it clear to see how all these are equivalent or the same. With the Krypton's approach, we have to linearize the metric perturbation, and we have to work with the linearized metric perturbation all through. So wherever we have the metric perturbation, we have to use this trace reverse metric perturbation, and that is the approach. With Weinberg, we did that just once. Like I said, subliminal, because Weinberg himself didn't even care to make that notation. It wasn't necessary, I believe, for him, but this is just what it was. This was the equation we had, but you can see that the right-hand side, this was the only linearized a trace reversed quantity defined. So to say, this was the trace reversed quantity, and with this, we simply just went ahead with the metric perturbation and no trace reverse notation. We didn't trace reverse it, we just worked with it, linearizing this equation all through until we obtained this solution. And so I call this solution a la Weinberg, that is by Weinberg's method, this is what you get. But however, with Krypton's method, this is what you're going to get. So I think maybe to make, okay, I did that here, but I think it would be better for me if I written this as that. So with Weinberg's method, you obtain the D'Alembertian of the metric perturbation equal to minus 16 pi g trace reversed energy momentum tensor. Now, but the Weinberg's method gives you here the D'Alembertian of the metric perturbation trace reversed equal to minus 16 pi, of course no g because g is set equal to 1. That is the Alaton, you have g to be equal to c equal to 1. So it's equal to minus 16 pi, but t mu nu not trace reversed. So you can see why it's really important to be able to make this identification. These two, I believe, are completely equivalent, but you have to be certain or understand what is going on. What you have on the right-hand side here isn't just the energy momentum tensor. If you worked with Weinberg's approach, what you have on the right-hand side is the trace reversed energy momentum tensor. But with the Krypton solution, what you have on the left-hand side isn't just the metric perturbation, but the trace reversed metric perturbation. But then your right-hand side, the source there is just the energy momentum tensor, not the trace reverse energy momentum tensor. So our Z, of course, I raised that. Z mu nu is the same as the trace reverse energy momentum tensor, which is equal to that. So in the end, just like we have already identified or written here, by Weinberg's approach, you obtain this. By Kipton's approach, you obtain that. Sorry, I know, of course, the book by Miss Nathan and Willa is written by 3 people, and probably I should be saying Miss Na, but I apologize for the inappropriateness. But hopefully, with all this identification, I hope also to have accorded every attribution as will be required of me in terms of all this lecture. So let them all be duly acknowledged for their very good works. So in what I'm saying here, the Lambashian of H mu nu is equal to minus 16 pi g T mu nu bar, which is the trace reverse energy momentum tensor. But then also another form of the equation which is completely equivalent or the same is that it almost looks like you should take the trace reverse tensor of both sides of the equation and you obtain the other one. So it's like you can see it as some kind of conjugation procedure by which if you perform the conjugation here, the trace reversal leaves this point or this part of the equation and moves over to this one. So of course in our solution, with what we have written, we named this Z sub mu nu last time, which again, like I said in Wemba's book, you will find this to be S sub mu nu. But you have to realize again, according to the notation we just introduced in this lecture, that this is the same thing as the trace reverse energy momentum tensor. So what you have here as the source is T mu nu bar. With Kipton's approach, your solution, rather what you are going to have on the left-hand side, is the trace reverse metric perturbation, not just the metric perturbation. And that will be equal to 4 times. Again, the G is missing because G is 1 in his own approach. And then, of course, you can see that the integral here, what is contained as the source is simply the energy momentum tensor and not the trace reverse as one will think or expect. So I think with this, we have been able to make comparisons of these two solutions in how they occur, how they appear. Let's hope and look into the next expression, what this is going to give. Okay, so it will be very interesting to see a summary of the formulae that we have obtained in the past few lectures, especially because it will be admirable looking at them. I believe they are a set of gorgeous equations. So first we have shown, of course, that the metric perturbation, which is this, can be used to sort of define the metric tensor in terms of the Minkowski tensor plus that. And when they are both contravariant, we get a minus sign here. We also have obtained and shown that the Minkowski metric written in that form, one of the indices raised, is the same as the chronicle delta. And of course, when we contract one of these two in 4-dimensional space, this gives us 4, just as we always know. And just like it is with metric tensors, this product is always equal to the chronicle delta. In our linearization of the Christoffel symbol, we obtain this expression here. Of course, because of the linearization, one can succinctly write the Riemann tensor in this form, this being equal to that. With the other terms, which are products of Christoffel symbols, which therefore will be products of, so it will be quadratic, so to say, in the metric perturbation. So as we said, those terms will be 0 and so they disappear. If we contract lambda and nu in this expression, we obtain this. And of course, plus higher order terms in H, quadratic and above. And if we raise the, we perform the coordinate transformation that leads to this transformation of the metric perturbation. And this is what we obtain in that case. And of course, we have the variant of it when we lower the indices, and this is what we get in that case. And so the Riemann tensor, of course, to be overly explicit, like we've stated from the other part, so we obtain a succinct expression. We can simply substitute the Christoffel symbols, the linearized Christoffel symbols, of course, and this is what we'll obtain. For the Ricci tensor, the linearized Ricci tensor is given by this expression. And the D'Alembert for this expression is given by that. So note again in this that, for instance, there is a comma below here. And after the comma, every other index that comes in, for instance, this might as well be written as comma with sigma and sigma here. In another notation, some may want to add comma here. Well, I don't want to clog things up, but however, sometimes when we talk about covariant derivatives, we may do that, but as of now, just take a note that anytime there is a comma, after the comma, whatever is left are just indices on the differential operators. And of course, our linearized Einstein field equation, we obtain to be this equal to that. This is mu nu, which we have in this lecture already defined to be the same thing, of course, with this, which is the same thing as the reverse trace tensor of the energy momentum tensor, reverse trace energy momentum tensor. And also z rho nu in this form, of course, with this raised, is equal to that. This is also one of the expressions. And like I've stated, of course, we already used this once. So this also is one of the expressions we obtained. And where this, well, of course, so you could get this. Okay, so it means with this, of course, you could write this in that form. Especially when you differentiate with respect to x rho. So we've already seen that. Another way of writing that is that, of course, with some other kind of notation. And then when we raise one of the indices on the Ricci, linearized Ricci tensor, we will obtain this. Of course, the raising of indices is always done with the Minkowski metric in this case, and not the metric tensor, the general metric tensor. Excuse me. Now we have that the trace of the linearized Ricci tensor is given by that. Or you may call that the Ricci scalar. So the linearized Ricci scalar really is what we have obtained. The D'Alembert of the trace of the metric perturbation minus double derivative, of course, of h lambda sigma comma lambda sigma. And of course, if we differentiated the mixed tensor, mixed linearized tensor of the Ricci tensor, or mixed linearized Ricci tensor, if we differentiate that with respect to x rho, this is what we will obtain. These are all this among the formulae that we obtained on that day. Also, we obtained this also here with comma nu equal to 0. And in that case, we were able to identify, we said, okay, that we could call this the linearized Einstein field tensor. So with this, of course, you can see it obeys also some kind of linearized contracted Bianchi identity. Differentiating this with respect to x nu gives you 0. And then, of course, also with this, the R1 rho nu equal to 1 over 2 R1 sigma sigma comma nu. Yeah, so this is, of course, just one of the, I think I've just repeated this because I think I've written this here. Okay, well, this is just another way because this R sigma sigma is given by that, this expression, which I believe not too long ago we have made mention of already. Okay, and that was somewhere here. This is it. R sigma sigma is given by this expression. So again, so, and one of these, this transformation here of the metric perturbation by raising one of the indices is also the same as that. And of course, our very famous harmonic coordinates condition, which gives us that by the product of our Minkowski metric and the linearized Christoffel symbol. And also this, the trace of that is given by that. We could also at the same time write this expression by making the subject of the formula. This we can see is the same thing as, okay, well, we're just trying to say that rho, sigma, or sigma down and rho on top are all the same. But from this expression, you can see, of course, we can show the divergence of this epsilon of x to be equal to that. Now, moving on, we had the coordinate transformation denoted by this, and we had a condition that had to be satisfied, which we just showed previously to be that. And of course, in that expression, what we had it to be is this, but of course, it's the same as that also. Now, looking at what we've got here, we want to look especially at the result that we've obtained. I think I might have made a mistake in terms of what I'm writing over there, because this here actually is what is equal to that. So I think I've made a mistake with this. Please strike that out. But what is correct is actually this. The sigma, epsilon sigma of s is what is equal to that. And this condition, remember vividly, to be equal to that. And of course, and then our sets of solution, what we actually worked with was with the approach again that we have mentioned before. And our initial approach was to work with what subliminally here we could call the reverse traced energy momentum tensor. We linearized this solution, and this was what we obtained as the solution for that for this equation, just analogous to the form momentum of classical electrodynamics. And of course, if you use the Kipton approach, you will have to solve this, and what you are solving for is the reverse trace metric perturbation. And with this, you have your source on the right-hand side again, like we said, to be the energy momentum tensor, whereas it is the reverse trace energy momentum tensor on this part. And you can see the solutions, of course. Here, we don't have any bar, but we have a bar here. We have a bar here, but we don't have any here. With G being equal to 1, again, in this case. And so this gives us finally what we wanted to discuss at this point. See you next.